In the last class, we obtained an expression for error in interpolation as this and bound on error in the interpolation as this. So, we shall consider some example and see how we can obtain such an error bound in this case. So, let us solve this problem. Suppose say we are given a function f of x is equal to sin x and it is approximated by a polynomial of degree 9 that interpolates the function at a set of 10 discrete points in this interval 0 to 1. The question is, how large is the error on this interval? Can you provide an estimate on the error bound is the question. So, let us work out the details. We are given f of x to be equal to sin x and we want to determine the error in interpolation when we represent this function sin x by a 9th degree polynomial which interpolates this sin x at a set of 10 distinct points. So, I have to compute, or let us first relate this formula with what we want and what we are given. So, we are given that the function is approximated by a polynomial of degree 9. So, we would like to find what is f of x minus p9 of x is. The theorem says it is equal to the 10th derivative of this function at some psi belonging to the interval open interval 0 1 by 10 factorial multiplied by pi 10 of x. What is this pi 10 of x? Pi 10 of x will be x minus x naught, x minus x 1, etc. up to x minus, what is n? N is 9. So, x minus x 9. So, it is a polynomial of degree 10. Where do these points lie? X naught, x 1, etc. x 9, they all lie in the interval 0 1 and x is again a point in the interval 0 1. So, when I want to determine the error bound, I require modulus of pi 10 of x. So, that will be less than or equal to 1, because modulus of x minus xi is less than or equal to 1 for x xi lying in this interval 0 to 1. I require the maximum of the absolute value of the 10th derivative of f, where psi belongs to the open interval 0 1. What is the function f? F is sin x in the interval 0 to 1. So, if you take derivatives, the first derivative is cos x, the second derivative is minus sin x and so on. So, the 10th derivative will be such that the maximum of the absolute value of that will be less than or equal to 1. And therefore, I have all the information that I require to compute the error bound, namely modulus of f of x minus p9 of x in this case is modulus of sin x minus p9 of x, and that is less than or equal to m n plus 1, and that is 1 by 10 factorial into modulus of pi 10 of x, which is again less than or equal to 1, and hence the bound on the error in interpolation is such that it is less than or equal to 1 by 10 factorial. So, how large is the error on this interval requires us to give some information on the error bound, and the result says that error in interpolation cannot be greater than 1 by 10 factorial. So, the inequality that we have obtained here on the error bound provides us a way of giving the size on the error bound for interpolation. So, let us now work out the details using this error bound when the points xi are equally spaced, and see what happens when I approximate the function f of x by a constant polynomial or a linear polynomial or a quadratic polynomial. In all these cases, we shall take our xi to be equally spaced and determine the error bound in each case. So, what is my question? My question is, I have a function f of x. I want to approximate this function by a polynomial of degree 0, namely a constant function. What does that mean? I am given information at one point, namely x naught comma f of x naught. So, my n plus 1 is 1, and so n is 0. I write down the error in interpolation in this case. This tells me f of x minus p naught of x is equal to f dashed psi by 1 factorial into pi 1 of x. So, that is f dashed of psi into x minus x naught. So, f of x minus p naught of x is f dashed of psi into x minus x naught. What is this p naught of x? P naught of x is a polynomial of degree 0. What is its property? It interpolates the function f of x, where at x is equal to x naught. So, its property is such that p naught of x naught must be equal to f of x naught. So, p naught of x is a polynomial of degree 0. So, it is a constant polynomial which is given by f of x naught. So, where does psi lie here? Psi lies in the interval x to x naught. Let us now work out the details when n plus 1 is 2 and therefore, n is 1. So, we are given information at x naught f of x naught and x 1 f of x 1. So, there are 2 points at which the information is given, and let x 1 minus x naught be h, and hence I can obtain a linear interpolating polynomial that interpolates the function f of x. So, f of x minus a polynomial of degree 1, which I denote by p 1 of x, that is equal to n plus 1th derivative of f, that is the second derivative of f at some psi divided by n plus 1 factorial. So, 2 factorial into pi 2 of x. So, what is it? It is f double prime at psi by 2 factorial into pi 2 of x will be x minus x naught into x minus x 1. So, this gives me the error in interpolation at any x which belongs to the interval x naught to x 1, and that is f double dashed at psi by 2 into x minus x naught into x minus x 1, and where does psi belongs to? It belongs to the interval x naught to x 1. So, can you give the bound on this error. Let us work out the details. I want modulus of f of x minus p1 of x. So, that will be less than or equal to m2 by 2 into modulus of x minus x naught into modulus of x minus x1. So, I am given information at x naught and x1, x is some point in that interval. So, mod x minus x naught is less than or equal to x1 minus x naught, and mod x minus x1 is less than or equal to mod x1 minus x naught. So, this will be less than or equal to m2 by 2 into x1 minus x naught the whole square. That is, it is less than or equal to, this is h according to our notation. So, h square by 2 into m2, which is less than h square into m2. So, modulus of f of x minus p1 of x can be made less than h square times m2. And what is m2? Modulus of f double prime of psi is less than or equal to m2. So, we have the error bound in case when we approximate f of x by a linear interpolating polynomial. So, let us consider an example and understand this result. The problem is to determine the step size h to be used in the table of f of x is equal to sin x in the interval 1 to 3. So, that the linear interpolation of sin x in this interval will be correct to 4 decimal places. So, we are given f of x is equal to sin x. And we want to find out the bound on the error in such a way that the linear interpolating polynomial that interpolates the function f of x is such that the result must be correct to 4 decimal places. We already have computed the bound on linear interpolation error. So, we shall make use of this. So, f of x minus p1 of x is less than h square into m2. So, we compute f dashed of x, that is cos x, f double dashed of x, that is minus sin x. And what is m2? m2 is such that modulus of f double dashed of psi is less than or equal to m2 for psi in the interval 1 to 3. So, we can compute the maximum of modulus of minus sin x for x in the interval 1 to 3, and that is going to be 1. So, we have all the information that is required, so that we will be able to answer this question. We get h square into m2 is 1, that must be less than or equal to 0.00005. From here one can compute the value of h. So, in the table of values of sin x, you consider points which are spaced at an interval of h units, where h square is less than this. Then, if you approximate sin x by means of a linear interpolation polynomial, then your result will be correct to 4 decimal places. That is what the conclusion is. When you approximate f of x by a linear interpolating polynomial, we have obtained the error bound as this. In fact, one can show the following result, namely f of x minus p1 of x in absolute value is less than or equal to h square by 8 into m2, where modulus of f double dash of psi is less than or equal to m2, where psi is in the interval of interest. So, let us prove this result in the case of linear interpolation. So, what do we know about f of x minus p1 of x? We already have worked out the details. That is going to be f double dash of psi by factorial 2 into x minus x naught into x minus x1. So, I shall write down h of x to be equal to x minus x naught into x minus x1 divided by 2, and that is x square minus x into x naught plus x1 plus x naught x1 by 2. So, h dash of x is 2x minus x naught plus x1 by 2, and it vanishes when x is equal to x naught plus x1 by 2. And in this interval x naught to x1, I see that h of x is, it is x minus x naught into x minus x1. So, I have the interval x naught to x1, x is somewhere here. So, x minus x naught into x minus x1 is going to be negative in this interval. In addition, I see what is h double dash of x. H double dash of x is going to be 1, so positive, and therefore, I have h of x to have a minimum in the interval, has a minimum in the interval x naught to x1. We have shown that h of x is negative in this interval, and h of x has a minimum in the interval x naught to x1. So, therefore, modulus of h of x has a maximum where in the interval at which point at x is equal to x naught plus x1 by 2. So, modulus of h of x has a maximum at the point x is equal to x naught plus x1 divided by 2. So, we can compute the maximum of h of x. What is the maximum of modulus of h of x? So, modulus of h of x is modulus of x minus x naught into x minus x1 divided by 2, and I want the maximum of modulus of h of x. So, maximum of modulus of h of x will be, where is it attained? It is attained at x is equal to x naught plus x1 by 2 minus x naught into x is equal to x naught plus x1 by 2 minus x1 divided by 2. So, it is half of modulus of, what do you get, x1 by 2 minus x naught by 2. Here again x naught by 2 minus x1 by 2. So, it is x1 minus x naught by 2 into 2. So, 4 the whole square. So, it is 1 by 2 into x1 minus x naught the whole square, but x1 minus x naught is h. So, it is h square by 8. So, therefore, modulus of f of x minus p1 of x is less than or equal to modulus of f double dash of psi, which I denote by m2, into maximum of x naught into x minus x1 by 2, and that is what is h of x, and that has been computed to be h square by 8. So, into h square by 8, and this is what we wanted to show. So, the error bound in linear interpolation is such that the absolute value of the error in linear interpolation is less than or equal to h square by 8 into m2, where modulus of f double dash of psi is less than or equal to m2 for psi in the interval x naught to x1. So, let us work out the same problem which we had done earlier, namely we have the function f of x is equal to sin x in the interval 1 to 3, and we want to approximate this function by a linear interpolating polynomial, and we want to use the set of values of xi and f of xi, which is sin xi, so that these points xi must be equally spaced, and use these to obtain an approximation to sin x, which is a linear first degree polynomial. So, what should be the step size h such that the result is correct to 4 decimal places? That was the problem which we had solved earlier, but we used a different error bound and obtained that my h should be such that h square is less than this. We shall now make use of this error bound and work out the same problem. So, as before, we have maximum of modulus of minus sin x for x lying between 1 and 3 will be equal to 1. So, I directly make use of this. So, modulus of f of x minus p1 of x, which is less than or equal to h square by 8 into 1, and my h should be such that I want h square by 8 into m2, which is 1, to be less than or equal to 0.00005, correct to 4 decimal places. So, that gives you h square to be less than or equal to 0.0004. So, h is less than or equal to 0.02. So, if you have a table of values of sin x at xi, which are equally spaced with step size h to be less than or equal to 0.02, then your result in approximating sin x by a linear interpolating polynomial will be correct to 4 decimal places.